Okay, looking at the print, I think what I'm going to do next, since I'm already set up for milling, is I'm going to mill out this notch in the middle here. So whenever I do something like that, mill a feature like that, I like to have a layout lines to follow, just so I don't go over. So just put some, you can use layout die, or if you like, or just, I like to use a Sharpie. Makes great layout die. So let's go ahead and lay these lines out. We need a line 980 from the back side. Let's go ahead and do that. Height gauge. It's hard to see because it's kind of cramped back here because the surface plate doesn't get used that much, so it shares space on the loading bench. Kind of tucked back in the corner here. Let's see, 980. There. Okay, then 438 from this edge. I don't know if all you guys have a height gauge or not. If you don't have a height gauge, you can do the same thing with a surface gauge. Alright, there's that line. And the next one's 3/4 of an inch farther. Which is 1.188 of there. Again, these are not, I mean, the lines are accurate, but we're not going to be relying on them. They're just guidelines to keep from milling too far and getting into, milling over the line, so to speak. So now we have that line laid out, so let's go back to the mill and mill that baby out. Okay, so now we have the slot laid out on this part, and what I'm going to use is a 5/8 2-flute end mill to hog that slot out. 4-flute would probably be better for steel, but I don't have one this size, so I'll use the 2-flute, and just be aware of the extra chip load on the tools and on the teeth. Since there's half as many teeth, there's twice the chip load, so you have to take a little bit easy when you're milling on it. Keep from chipping teeth. There's two ways I can hold this thing. I can hold it like this, and I can mill it in this direction, or I can hold it like this and mill it in this direction. This is the preferable position, and I'll tell you why. If you put it in the vise like this and you start to mill that way, when your end mill touches the part, it's going to want to force the part sideways. And since there's nothing keeping it from going sideways except the friction between the vise jaws and the part, sometimes your part, when it's positioned like this, can rotate, which is a bad thing. So what I do in something like this is I'll turn it this way. Now, if we run the end mill into the part this way, it's going to force it against the solid jaw of the vise, and it can't go anywhere. So it's much more stable setup. Let's mount the thing in the vise like this, centered up on the jaws. Put it down against the parallels. Whoops, that wasn't quite tight. Okay, now we're going to be working off of, which one? Let's look at the print here. It's going to be working off from this surface, so let's pick up that surface with the edge finder. Run your edge finder in until it kicks sideways. Zero out the dial, or the digital readout in this case. Offset half the diameter of the edge finder, which in this case is 100 thousandths. And that puts the center of the spindle right on the edge of the part. So now, let's put the end mill in. And I'll show you how I like to cut slots with an end mill. I don't know how sharp this end mill is. I guess we'll find out soon enough. Alright, the way I like to cut slots is I like to touch the edge of the part, then move over to the center of the slot, and then reset my digital readout. So the center line of the spindle is on the center line of the slot. Then I can offset the end mill each direction to get the width. So it'll need to go about a 1/16 inch in each direction. We'll figure that out, what it is exactly in a minute here, but that's the way I like to do slots. I'll show you how it's done. Okay, so the center of that slot is 0.438 plus half of the 3/4, which is 3/8. So 0.438 plus 0.375 is 813. So let's move in 813 thousandths. Right there. Okay, now I'm going to zero out my digital readout. And then when I then I need to figure out how far each direction to move the end mill to get my 751 plus 5 minus nothing slot. And the way you do that is you take 0.751. Let's add about half of this tolerance to it, half of the plus 5, so add 2.5 thousandths. So that gives me 753.5 for the width that I'm shooting for. That'll put me in the center of my tolerance. And I'll subtract from that the diameter of the end mill, which is 0.625. Okay, so I have to take 128.5 thousandths worth of material off, but only half of that on each side, so let's divide by 2. So I need to move the end mill each direction 64.0643 thousandths. So let's go ahead and get started on this slot. I'll run the end mill down against the stop near the top of the part, and feed the table up till the end mill just touches the top of the part. So we have a starting point for the depth of the slot. Right about there. Zero out my dial. We need to go, what's the depth of the slot? 2 inches minus 980. So the slot is 1 inch 20 thousandths deep. I'm going to crank the table up 1 inch and 20 thousandths right now. Then I'm going to reset my dial to 0 so I know where the bottom of the slot's supposed to be. Then I'll drop the table 10 thousandths to leave room for a finishing cut. Okay, now I'm gonna rough this slot out. All right, make sure everything's tight. And the way I like to rough slots out, especially in steel, is to plunge cut it. If you just end mill through, it's a lot harder on the end mill. Generates more heat, takes longer to do. What I like to do is, well, first of all, when I bump this part, it's going to force the part in that direction. So I want to take any play out of the Y lead screw on the machine. So I'll back my dial up counterclockwise to remove any backlash in the screw. So if the table can't move, then it's against the screw. Alright, so let's do that. Let's check the diameter. It should be a 5/8 end mill in steel, should be about 600 RPM. It's a little bit fast. Let's slow her down to about 600 or so. And we'll just plunge the depth of the slot a little bit at a time, move over, plunge, and work your way through this way. Your end mills, if you cut deep slots like this, your end mills will last a lot longer than if you're trying to end mill them sideways, side mill them. It wouldn't hurt to lock the table in the Y direction as well, especially on a lighter mill. Not too worried on this one because I got all the backlash taken out of the screw, so there's no place for it to go. But on a lighter milling machine, it'd be a good idea to lock the table and take the backlash out of the screw. See, the chips are coming off. There's no color to them, so they're not overheating. Not overheating our end mill. If we were side milling this deep of a slot, I can guarantee you those chips would be coming off colored. Takes care of roughing it out. Run it back through to take any of the high spots off. Now we can move each direction, or what did I say? I don't know how much I said. 64.3 thousandths. I'm going to conventional mill my first pass. Move over about 54 thousandths. Lock the table down. Now I have to be a little bit careful because we're back to forcing the part sideways again. So don't try to take too much metal off at once or try feeding it too fast. You don't want to tip the part. You always have to be aware of what direction the tool is trying to force the part when you're milling. That way you can Be sure to take any backlash out of the screws, or figure out what the best way to hold it is. All right, 54 thousandths the other direction. We'll come back. This would be a bad time to try climb mill on a part like this, because if it grabbed it all, then it would want to rotate the part, kind of pull the part into it. That's why I'm conventional milling. I'll climb mill for the finished pass, but for roughing out, conventional milling. That way, if the part does start to move, I can see it and I can stop. I won't grab the part and pull it into the cutter. All right, there we are. We're all roughed out. Okay, now I'll move back over to this front side. We'll go in 60 thousandths. We want to end up at 64.3. I'll go to 60. And also drop down to the finished depth. Actually, I said I was going to climb mill, so we'll do it on the back side. We'll go 60 to the back. Now we're milling on the back side. The cutter's trying to climb up on the part. And we're only taking a shallow cut, so it's fine. And I will do the same thing on the front of the slot. 60 thousandths to the front. If you're doing this with a light bench mill, ignore what I just said about the climb milling, because you wouldn't want to do that, because the mill's not rigid enough to support it. You want a conventional mill the whole thing. You want to make sure to take all the backlash out of your lead screws and lock the table down as well to control the cutter. Alright, now I'm going to do the same thing. I'm just going to repeat it at the same setting, just to take any spring out of the end mill. Then I'm going to check the width of the slot. Alright, 60 thousandths. Cutting on the back side. Now move it to the front, 60 thousandths. Take a spring pass on that. Right there. And I'll show you an easy way to measure the width of a slot. This is a pretty critical width on this slot. It has a +5 -0 tolerance on it. So it's I wouldn't want to measure it with a dial caliper or a vernier caliper or a digital caliper. It's not going to be reliable enough. What I like to use is a adjustable parallel, like this. Okay, we just find a parallel that'll fit in the slot, expand the parallel till it touches the side of the slot, then mic over the parallel. I'll tell you exactly what the width of that slot. And since we're putting a part in this slot, if there's any high spots on it, we have to count those as part of the width. So the adjustable parallel will hit any high spots and tell you the true width of the slot. In this case, it's 744 thousandths. 744, and we want what did I say? 750. 750 plus 2.5, 751 plus 2.5, so 753.5, and we're at what did I say? 44.7535 minus 0.744. Got 9.5 thousandths to go. Divide by 2, we have to go 4.8 thousandths each direction. Get this parallel out of here. And we'll finish it up. We'll go back, we have to go, we're 60 thousandths before, so now we're going to go 64, we'll go 65 thousandths. I think that'll be pretty good. Right there. I'll lock my table down. It should be taking about 5 thousandths off of this back surface. We'll do the same thing to the front, 65 thousandths. There. Alright, let's see how we did. Your adjustable parallel back in, expand it till it locks in the slot, like the parallel. You should be a little bigger than 751. We are at 752.5. So that's the size. Let's drop the thing down in the bottom of the slot. Make sure it's not tapered. Okay, see we got a little bit of taper going here. The bottom of the slot's 751. So I am going to take another spring pass on the slot just to make sure, get some of that taper out of it. Do the 65 thousandths cut again. On the front. That's what happens on slots. The end mill flexes and you end up with a tapered slot. I expected that. From experience, that's why I checked at the bottom of the slot as well as the top. Okay, let's see if that was enough. I don't care about the top now. We know that's good. Go down the bottom, we need to be bigger than 751 to the bottom to make our tolerance. We're a little over 752, we're good to go. So that is the slot. Let's go ahead and deburr it. Alright, looks pretty good. Deburr all the way around so I don't slice my finger open handling it. Knock the corners off. Alright, we're starting to look like the part. Alright, so next I think we'll probably do some drilling while the thing is still relatively block-like. We'll go ahead and put all the drilled holes in it. And then probably we'll mill the radii, and then I'll go back and put these steps in. So let's set up and drill some holes.